Hey everybody, welcome to section 2.4. Um, we've got a lot of new and interesting stuff coming at your way here. You might want to duct tape your brain together because there's going to be a lot of stuff. But I actually want to start with what's the difference between average velocity and instantaneous velocity, and how do you find each? Okay, can you answer that question? Well, I know that average velocity is the average rate of change in position with respect to time. And it's always on an interval from A to B. And so the way I would find that is S of B minus S of A over B minus A, because we know that rate of change is slope with units. So that's how I find average velocity. Notice S, these are position values. I find the y value at B, the y value at A on the position graph. I plug them into the slope formula, and I can find the average rate of change between those 2 points. Okay. So we often describe that as the slope of the secant. Slope of the secant. So when I think about a graph and I think about a secant line touches a curve in 2 places. So A, B, here's my position function. And so if I want to know the average rate of change or the average velocity on A to B, I do S of B minus S of A over B minus A. That finds my average rate of change. In this situation, because I'm talking about position, it could also be the average rate of change in position with respect to time, and we know that's the definition of average velocity. Okay, just like average acceleration would be the average rate of change in velocity on A to B. And so we would do average acceleration equals v of B minus v of A over B minus A. Some students confuse these and think that this finds average velocity. No, that finds average acceleration. This finds average velocity just using the slope formula between 2 points on which function? On the position function. That finds average velocity. If you want average acceleration, you need to find the slope between 2 points on the velocity graph. Okay, so that's average velocity. What about instantaneous velocity? Well, we said instantaneous velocity would be the slope at a point, not on velocity, but on position. So we said that we could use prime notation. S prime could be velocity. V prime could be acceleration. But acceleration could also be s double prime, the rate of change in the rate of change in position with respect to time. I bring this up now because when I think about this being a position function, and I want to know what's my velocity at t equals 2, what I really need to find out is what's the slope at t equal to 2, because that's going to be the instantaneous velocity at 2. So slope of the tangent line at a point is going to give you the instantaneous velocity. Okay? Now, right now, what methods do we have for finding the slope at a point? Well, until today, the closest we could do was find 2 points wicked close together on the curve and put them in the slope formula. This is a method that nobody likes, and this is how we can find instantaneous rate of change. So today, I'd like to give you a much easier way to do it that doesn't require us to use these wicked close inconvenient points. Okay? That's going to be our big goal for the day. So, let's see if you can apply what we've been talking about. Question. Here's some population data from Taiwan. 2010, 23.16 million, 2011, 23.22 million, 2012, 23.32 million, 2013, 23.37 million, 2014, 23.43 million, 2015, 23.49 million, and 2016, 23.53 million. Okay, so these are millions of people, and these are years. You may want to do t equals 0. I mean, it's not going to matter for what we're going to do. Never mind. Okay, so the question is, what's the average rate of change in Taiwanese population? I think that's one S. Population. Oh, running out of board. On 2010 through 2016. Okay, please find that average rate of change in Taiwanese population. Well, I hope you didn't find this one too difficult. If you haven't tried it, give it a try now. Pause the video and come back. But I know that average rate of change is slope with units. And so I'm going to be using these pieces of information to find my slope with units. 2353 minus 2316 over 2016 minus 2010. So what do I get? 53 minus 16. I get 37 million. And on the bottom, I get 6. So 0.37 divided by 6 equals 0.0616 And don't forget the units. So we have millions of people on top, and we have years on the bottom. So 0.0616 million people per year. The average rate of change is that. Now, it may be that instantaneous rate of change is bigger than this number or is smaller than this number. But I know that the average rate of change from here to here is 0.0616 million people per year. Okay, so how could we estimate, and the key word here is estimate, the instantaneous rate of change at t equals 2012? Well, here it's only an estimate, it's only an approximation, and I can't get wicked close like I did on the microscope worksheet, but I could choose a couple of paths here. I like that, well, I like actually my favorite method is I can find the slope between these 2 points. I could find the slope between these 2 points, or I could skip 2012 and find the slope between those points. Okay, so I have 3 different things I can do to get this estimate. I actually think I like best a 4th plan, which is to find the slope from 2011 to 2012, find the slope between 2012 and 2013, and then average those 2 numbers. So from 2011 to 2012, what will that computation look like? 23.32 minus 23.22 over 2012 minus 2011. Well, that's nice because that's only going to be 1 year. And so I have 0.10. Okay, what about on the next interval? What would that look like? 23.37 minus 23.32 over 2013 minus 2012. And when I do that, I get 0.05. And so now what I'm saying is, I think that is an approximation of the instantaneous rate of change. That's an approximation of the instantaneous rate of change. But I'm arguing that if I average those 2 numbers, that I get a more accurate instantaneous rate of change. Okay? Tables are great for average rate of change, and they're not very good for instantaneous rate of change. I mean, the table values are only the table values, and I definitely can't get wicked close. Okay, so let's see if we can transition to a way to actually find instantaneous rate of change. Or the slope at a point. So in the past, we said, we got this function, I want to know the slope here at A, there's the ordered pair A, f of A, and I want to know the slope there. And so we would pick this point, wicked close to that point, and imagine that we could find the slope between those 2 points. Now, even though we have this wicked close point, very near A comma f of A, we're still not getting the actual slope at the point. This is still just going to be an approximation. Well, let's consider this. Let's imagine we have this point here called x comma f of x. And then we go over a little bit. Let's call that little bit h. And we get to this other point over here. Now, this distance is called h. So this ordered pair up here is going to be what our x value was plus h. And then what about the y value here? Well, x plus h has to be plugged into the function. Okay, so my y value is f of x plus h. Great. So now, what does it look like if I use the slope between these 2 points? So slope, or instantaneous, no, I can't even say that yet. I'll come back to that in a minute. So the slope formula will be f of x plus h minus f of x over x plus h minus x. That's my slope formula. I can tidy up the bottom, can't I? F of x plus h minus f of x all over h, because these x's cancel. Now this finds the slope between 2 generic points on the curve. But what I'm looking for is not the slope of the secant, because that's clearly what I have here. This is the slope of the secant between these 2 points. Okay, I'm trying to find the slope at a point. So here's what I have to ask you. If I'm talking about finding the slope at a point, using these 2 points, what has to be true about h? I'm not trying to find an average rate of change. That's what this does. I'm trying to find the instantaneous rate of change. I want to know the slope at one point. What does h have to be in order to let me have the slope at a point? Well, h has to approach 0. So, while this is average rate of change, imagine what happens if we bring this point closer and closer and closer so that h gets smaller and smaller and smaller. In fact, h heads to 0. Well, now we can say this. We can say that the limit as h heads to 0 of f of x plus h minus f of x all over h. This is instantaneous rate of change. It's not an approximation anymore. It's the actual slope at a point. How do I find the slope at a point? I use my slope formula, but I let the distance between the 2 ordered pairs head to 0. Okay, so let's think about that. We've got slope at x equals a. Okay, that's what I want to find out. So I've got my curve, I've got my point a comma f of a, I've got another point up here where I went over an amount called h. So this is a plus h comma f of a plus h. So I've got these 2 ordered pairs. I want to know the slope at that point. And if this is f of x, we used a notation on the microscope worksheet where we said the slopes of f are called f prime. So I'm looking for f prime of a. And f prime of a is going to be the limit as x heads to, no, that's a different one, as h heads to 0 of f of a plus h minus f of a all over h. Now, curiously, if I plug a 0 in here, I'm going to get f of a minus f of a, which is 0. And if I plug in a 0 in here, I get 0 over 0. This is an indeterminate form. And that's why we had to start talking about indeterminate forms in this unit because when we start reaching out for the slope at a point, we get ourselves into that 0 for 0 situation. No worries though, in these next problems, you're going to be okay and fine with this, and we're not really going to be dwelling on this, okay? So let's continue. If, because we've got some variations on this, the slope at a point x equals a. We said that f prime of a, that's the slope at a, is equal to the limit as h heads to 0 of f of a plus h minus f of a all over h. Now, this f prime we know is the slope at that point. It also has another name. This is called the derivative. And what we're finding here is the derivative at a point. All our primes are derivatives, and they represent instantaneous rate of change at a point. Okay. So what if we didn't want to have just the slope at a point? What if we wanted to know all the slopes? Excuse me, I have to take this. Hi, Dave Kukla. Yes. Yes, sir. So yes and no. I'm actually, you're about to be YouTube popular because I'm taking this call while I'm recording a lesson for my students. But I should be out in about 20-25 minutes if that's great. All right. Okay, fine. Okay. All right, so derivative at a point is f prime of a. But what about f prime of x? Okay, we already saw it. It's the limit as h heads to 0 of f of x plus h minus f of x all over h. What I like about this form is this is called the general derivative. And what it allows me to do, I can plug points into x. So what does that help me do? Well, if I want to know the slope at only one point on a function, then I might use this, because this finds the slope at only one point. It's a single-use tool. I can only find the point at only that point. I mean, I can only find the slope at x equals a. This builds a general derivative when I'm done with it, and then I can plug all kinds of points into that. So this, I find, is really useful and helpful if I need to find the slope at more than one point on a curve. Okay, so right now, this is the limit definition of the derivative at a point. This is the limit definition of the general derivative. And I'll make clear more of those once we get to examples. I do, however, have one more f prime of a to show you. Okay, this is the slope at a point x equals a. Well, let's go back to our picture and let's envision this situation where I have this ordered pair called a, f of a, and then I have this point here. It's any point whatsoever on the curve. It's a general point, x, f of x. Well, I need to take this distance between these points and turn that distance into 0. So what has to happen to this point? Well, I have to make this come down, come down, come down until it's at that place. So when I think about a limit, it's not h that's heading to 0, it's x that's approaching a. I want x to get smaller and smaller and smaller until it is a. And then I'm just going to use my slope formula, f of x minus f of a over x minus a. Ta-da! There's my other slope at a point. And again, this only finds the slope at the point x equals a. It's a single-use tool. Sometimes that's all I need is a single-use tool. But other times, that's not going to work out so well for me. So I like the general derivative as well. So let's just list these again. We said f prime of x is going to be the limit as h heads to 0 of f of x plus h minus f of x all over h. This finds the general derivative. F prime at a point, though, is the limit as h heads to 0 of f of a plus h minus f of a all over h. And then we had a second way of finding the slope at a point, and that was the limit as x approached a of f of x minus f of a over x minus a. So, two ways to find slope at a point, and this is our general derivative. And I think this is fabulous if I have to find the slope at more than one point. Okay? So let's dig in. Okay. Say y equals x squared is our function. In fact, f of x is our function, and I want to know what is the slope of f of x at x equals 3. So what I'm asking for is, what's f prime of 3? What's the slope of f at 3? And we've got 3 different ways to find it, and you need to be all comfortable with all 3 of them. So the first one, if I'm going to find f prime of 3 directly, I might say the limit as h heads to 0 of f of 3 plus h minus f of 3 all over h. Okay, so how do I find f of 3? Well, here's f of x. F of 3 is I replace all the x's with 3's. So f of 3 is 9. What about f of 3 plus h? Well, now I have to replace this x with 3 plus h. So 3 plus h squared, or 9 plus 6h plus h squared. Okay, now that I found f of 3 and found f of 3 plus h, I have to subtract them. So f prime of 3 equals the limit as h heads to 0 of 9 plus 6h plus h squared minus 9 all over h. Okay, so what happens? Well, 9 minus 9, those cancel out. And then I've got the limit as h heads to 0, 6h plus h squared over h. But if I do direct substitution here, I still get 0 over 0. So let's take it a little further. Let's say the limit as h heads to 0 of h, 6 plus h over h. Then I can cancel these, and now I can do direct substitution, and I get 6. So I know the slope at x equals 3 on x squared is 6. That's the slope of the line. That's the slope of the tangent line, which is the same as the slope of the curve at x equals 3 on y equals x squared. We used one limit definition of the derivative here. Let's go use the others. Okay, so the next one, f prime of 3, that's going to be the limit as x approaches 3 of f of x minus f of 3 over x minus 3. Okay, so how do I find f of 3? I plug 3 in for all the x's of f of x. So f of 3, we know is 3 squared or 9. And what about finding f of x? Ah, no problem, there is f of x. So this is now going to look like the limit as x approaches 3 of f of x is x squared, f of 3 is 9 over x minus 3. Again, if I try and evaluate now, I end up with 0 over 0. Luckily, though, we spend some time working on our algebra skills to rewrite limits. So this will be x minus 3, x plus 3, over x minus 3. Aha, I can cancel those. And now I can take this 3 and plug it in x, because x is approaching 3. That means that's going to become a 3. I'll have 3 plus 3, or 6. And that's the slope of the point. But wait, what about using the general derivative? So if I'm finding the general derivative, I want to know what f prime of x is. And we said before that that would be the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, so let's see what happens. F of x, no problem. I just plug my x squared in there. But how do I find f of x plus h? Well, I have to replace all the x's of f of x with x plus h. That's an x in f of x, so that's going to be x plus h squared, or x squared plus 2xh plus h squared. So now I can rewrite this f prime of x, this general derivative, as the limit as h approaches 0 of x squared plus 2xh plus h squared minus f of x, here's f of x, all over h. Okay, so what happens here? The x squareds cancel out, and so now I have f prime of x equals the limit as h heads to 0 of 2xh plus h squared over h. And again, if I try and plug in 0 for h's, I get 0 over 0. So I think I need to do a little more. How about the limit as h heads to 0 of h, 2x plus h over h? Because then I can cancel those. Now I can do direct substitution. I get 2x plus 0, or 2x. That's what f prime is equal to. F prime is equal to 2x. So that's my general derivative. If I want to know the slope at any point on f, I just plug that point into f prime of x. So I want to know f prime of 3? No problem. I just plug a 3 in and get my 6. But what if I want to know f prime at negative 2? Well, I'd have to redo the limit definitions of the derivative at negative 2 now, but since I have the general derivative, I can say f prime of negative 2 is simply 2 times negative 2, or negative 4. So the slope on f at negative 2 is 4. These derivatives find slopes at points, okay? So what are you supposed to do with this? Well, you're supposed to become masterful of this. So how about this one? What if f of x equals 1 over x? And what if I want to know the slope at x equals negative 1/4? I want to find the instantaneous rate of change. I want to find the slope at x equals 1/4. So, will you please find for me f prime of x using our limit definition of the derivative? You don't know what that is. Yes, you do. It's the limit as h heads to 0 of f of x plus h minus f of x all over h. So please use this limit definition of the derivative with this f of x function to find f prime of x. Don't worry about slope at a particular point yet. We'll come to that in a minute. Why don't you pause the video, find the derivative by using this limit definition of the derivative. Okay? Pause the video and come back. Welcome back. So I need to find f of x plus h, and this is my f of x, so I'm going to plug in x plus h for all those x's, and that's what I get. I also need f of x, which is given to me as 1 over x. So now I can say f prime of x is going to be the limit as h heads to 0 of 1 over x plus h minus 1 over x, all over h. Ew. Well, I need to make a common denominator here. That's really what I need to do next, and then you won't be saying ew as much. So this needs an x over an x, and this needs an x plus h over an x plus h. See this minus? Make sure when you distribute that minus to the x that you also distribute that minus to the h. So our next line looks like this. F prime of x equals the limit as h heads to 0 of x minus x plus h all over x plus h all over h over 1. Well, so a couple of things. I don't like complex fraction where I have a fraction over a fraction, so instead I'm going to flip and multiply. So this is times 1 over h. All right, now what else can I do? Well, if I distribute on top, this line is going to become minus x minus h. And that's kind of cool because I see that the positive x and the negative x cancel. Okay? Now, I also see, look, this h and this h, these cancel. So I'm left with negative 1 on the top and x times x plus h on the bottom. But don't forget, this is still a limit. This is still the limit as h heads to 0. And yes, you have to write limit every time until you evaluate that limit. So now I'm ready to plug a 0 in for h, and that's going to give me f prime of x equals 1 over x plus 0, which is 1 over x squared. That's f prime of x. Now, how can I use f prime of x to find the slope of f at x equals negative 1/4? Well, that's easy peasy. All I have to do, having found the general derivative, is say, okay, if the general derivative is negative 1 over x squared, I believe it was negative 1 over x squared, because it was negative 1 over x squared, then to find f prime at negative 1/4 simply means that I come over here and plug a negative 1/4 in and square it. So negative 1 over 1/16, and when I do the flip and multiply, I get that, and so I know that f prime negative 1/4 should be negative 16. Okay? The slope on f at negative 1/4 is negative 16. So let's think about that graphically for a moment before we look at the other limit definitions of the derivative. Here's my graph of 1 over x. Whee! Whee! And so what we're saying is here at negative 1/4, the slope is negative 16. That's what f prime of negative 1/4 is telling me. The slope on f at negative 1/4. Using my limit definition of the derivative, which I find so much easier than using those wicked close points approach that we used on the microscope worksheet, the limit definitions of the derivative can definitely help me find that. All right, so what about, we still have f of x equals negative 1, positive 1 over x, and I still want to know the slope at x equals negative 1/4. But this time, I want to go directly to finding f prime of a. And why don't we use the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, so for us, we want f prime of negative 1/4, so I have to replace all the a's with negative 1/4. So that's going to be the limit as h heads to 0 of f of negative 1/4 plus h minus f of negative 1/4 all over h. Well, in order to make this different quotient work, what do I need? I need to know f of negative 1/4, which means I'm taking a negative 1/4 and plugging it into that x of f of x. So I've got 1 over negative 1/4, which is negative 4. I also need to find f of negative 1/4 plus h. Well, that's going to be 1 over negative 1/4 plus h. Remember, in this situation, I need to have a common denominator, before I flip and multiply. So here I'm going to multiply by 4 over 4. So now I've got the limit as h heads to 0 of 1 over negative 1 plus 4h all over 4. Okay, so, oh, no, I don't have a limit. That's just f of negative 1. Oh, and I can flip and multiply, can't I? 4 over negative 1 plus 4h. That's f of negative 1 plus h. This goes in here. This goes in here. All right, well, let's see where that takes us. So f prime of negative 1/4 is going to be the limit as h heads to 0. F of negative 1/4 plus h is 4 over negative 1 plus 4h minus f of negative 1/4 is negative 4 all over h. Ew. Now I know why we spent time working with complex fractions last year in pre-cal. So now I've got two things up top, and I need to make a common denominator so I can add them together. So I need a negative 1 plus 4h, negative 1 plus 4h. Okay, so now f prime of negative 1/4 equals the limit as h heads to 0 of 4 plus 4 times negative 1 plus 4h all over negative 1 plus 4h all over h over 1. And rather than have this complex fraction, I think I kind of want to flip and multiply here. So let's flip and multiply 1 over h. All right, let's see what happens when we type up this numerator. We have the limit. The limit as h heads to 0 of 4 minus 4 plus 16h all over negative 1 plus 4h times 1 over h. Okay, so what happens? These cancel. And this cancels with that, because I've only got one thing on top now. So now I have the limit as h heads to 0 of 16 over negative 1 plus 4h. And it's at this point, once I've canceled out those h's, that I can plug my 0 in for h, because it says h is approaching 0, so put a 0 there. And you get 16 over negative 1, or negative 16. Ta-da! So, wow, that was a pain in the butt. I'd rather find the general derivative. The general derivative was much easier. Well, that's true often, but not always. Let's take a look at finding f prime at negative 1/4 by using f prime of a equals the limit as x approaches a of f of a, no, f of x minus f of a over x minus a. We'll use this third definition of the derivative at a point. Okay, so if I want this, I have to replace the a's with negative 1/4. So now we have the limit as x approaches a of f of x minus f of negative 1/4 all over x minus a negative 1/4. Okay, f of x is easy. That was given to me. F of negative 1/4 we had to find by plugging negative 1/4 in there. So f of negative 1/4 is going to be 1 over negative 1/4, which is negative 4. Okay, so let's do it. We know f of negative 1/4 is negative 4. We know f of x is 1 over x. So our next line will look like this. The limit as x approaches negative 1/4 of 1 over x minus negative 4 over x minus a minus 1/4. Right? Because that's f of x minus f of negative 1/4 over x minus negative 1/4. This is just the slope formula with this function at that point. All right. So if I plug in negative 1/4 now, I get negative 4 plus 4, 0 on top, negative 1/4 plus 1/4, 0 on the bottom. So clearly, I'm going to need to do some algebraic manipulation here, like multiply this by x over x. And here, 4 over 4. So now, f prime of negative 1/4 equals the limit, as x approaches negative 1/4, of 1 plus 4x over x over 4x plus 1 over 4. Look, complex fraction. So what I'm going to do is flip and multiply. So now, f prime of negative 1/4 is going to be the limit, as x approaches negative 1/4, of 1 plus 4x over x times 4 over 4x plus 1. And I notice that these are the same. So this then brings me to the limit, as x heads to negative 1/4, of 4 on top, x on the bottom. All right. Now, what am I supposed to do? Well, x is supposed to approach negative 1/4. So I'm supposed to put a negative 1/4 in that x. So I'm going to have 4 over negative 1/4. When I do my flip and multiply, I get negative 16. So we did 3 different ways to find the slope on f of x at x equals negative 1/4. All right? And guess what? You need to be able to do that. You'll see the limit definition of the derivative not only in Chapter 2, but we see it again in Chapter 3, and we certainly see it again next March when we're starting our AP review. Okay? So, f prime of x means derivative. F prime of x means the slope at a point. Well, I'd like to take a moment to show you how to do slope at a point on your calculator. Of course, if you have a newer calculator, it's going to look a little different, but you're going to find it in the same place. So if I want to know f prime of negative 1/4 when f of x is equal to 1 over x, I can come over here to my calculator and type in 1 over x for f of x, and then I can do second, calculate dy dx. dy dx is a synonym for f prime of x. It's the change in y over the change in x. So when I see this notation, it's a synonym for this. It's a synonym for what is the derivative. In fact, not only could we see dy as delta y and dx as delta x, change in y over change in x, like we talked about with assignment 6 with increments, we could also take a more casual approach and say the derivative of y. But I don't like that because the derivative, I'm not doing the derivative of x. Okay, so there's my f prime of x. What do I want to do? I want to be able to find f prime of negative 1/4 on the calculator. Okay, so you go to Math, and then you scroll down until you see n-deriv. N-deriv is what we're looking for. Again, press the Math button, and scroll down to n-deriv. Enter. Now on the older calculators, it says n-deriv, and then it gives this parenthesis. And what it's waiting for you to say is, I want the derivative of what's in y1 in terms of x at negative 1/4. Okay, that's old calculator notation. New calculator notation, I'm not sure what they do. I think they do d blank, and then they say blank, and then I think they say x equals blank. I think that's what your newer calculators say. And this, in our class, will always be an x. And this is our y1. Or you could type in the function f of x. And this is negative 1/4. Okay? So new calculator, old calculator. Let's see what the answer gives me. I'm going to type in y1, comma x, comma, where do I want to know the derivative? At negative 1/4. Huh, what's that? That's unexpected, because that's rounding error. We did the exact derivative, and we know it's not that. Huh, I'm kind of surprised by that. What you doing there, calculator? Well, an interesting thing about the calculator is that does um, it does one-sided derivatives and then averages those two numbers together. Um, that's very interesting. I'm just going to look at that again. N deriv y1, yes, that's y1. N deriv y1 in terms of x at negative 1/4. Yeah, that should just be negative 16. Hey, let's try over here. Let's, because there's a second way to find the derivative. I don't like this other way as much because it's often more off than this one. So let's see our negative, our 1 over x, and let's do zoom standard. Okay, there we go. That's our reference graph that we're expecting. Now, go over to second calculate and scroll down to dy dx. Now, it's saying that's your function, and I need to type in where I want to know the derivative. So I type in negative 1/4. Hey, look, it's 16 and change too. That's so funny. Because we know it's 16. We know that the derivative of this, we know that the general derivative, f prime of x, is negative 1 over x squared. And so f prime of negative 1/4 is not going to be approximately, but exactly negative 16. That's very interesting. Huh. Well, be cautious about using the calculator. I hope those of you with newer calculators didn't get that weird extra decimal stuff instead of the exact negative 16 that you should get. I will say, though, that you will do a lot of derivatives by hand, and occasionally you'll do the derivative with your graphing calculator. Okay, so wait, there's just a little bit more. Find the equation of the tangent to y equals 1 over x at x equals negative 1/4. So what information do I need to write the equation of a tangent line? Well, I need a point. That's going to be f of negative 1/4. Well, when we plug negative 1/4 into f, we got 1 over negative 1/4, or negative 4. So now I have this point. What else do I need in order to write the equation of the line? I have an ordered pair, I have a point, but I also need a slope. Well, in our class, we're going to say, I need f prime of negative 1/4. Well, we know that f prime of negative 1/4 is negative 16. We've done it 3 different ways now. In fact, I think we did it 5 different ways because we did it on the calculator 2 ways. Okay, and what am I supposed to do? I'm supposed to write the equation of the tangent line. Well, that's easy enough with a point and a slope. Y minus 4 equals negative 16, x minus 1/4. And you can stop there. That's our tangent line. Our tangent line is simply this point-slope form where we use slope and point and plug them in. If you do want to tidy this up, y minus 4 equals negative 16x. This is minus 4, and now I get y equals negative 16x. That's my tangent line equation, is the tangent line to f of x at negative 1/4. Alrighty. Now, what if instead of asking you for the equation of the tangent line, I asked for the equation of the normal? Do you remember normal lines and tangent lines? Normal. We know that the normal, the slope of the normal, is 1 over the slope of the tangent. And we know slope of the tangent is this thing. It's f prime. So what do we want? Well, we want not this slope, but we want the slope of the normal. Oops, I forgot that. Which is the opposite reciprocal of this. So positive 1 over 16 is the slope of the normal. So when I go to write my tangent line equation, I still need a point. I'm sorry, when I go to write my normal equation, I still need a point. The point is still negative 1/4, but the slope of the normal will get changed to 1 over 16. And so y minus 4 equals 1/16 x plus 1 over 64. And then I could add 4 to both sides. Y equals 1/16 x plus 3 and 63 64ths. No, I'm adding 4. 4 and 1 over 64. That's the normal line. This is normal to this at this point. Okay, great. So what does that mean in my universe? Well, one, you're going to write a hell of a lot of tangent line equations in this class. Every chapter, we're going to write a tangent line equation. Normals, we're also going to write, but a little less frequently, but enough so that you need to remember that writing the equation of the tangent line and the normal line, wow, those equations look the same except for the slope. The slope is the only thing that's going to change when we're writing a tangent line versus writing a normal line, okay? Now, we will be, I promise, practicing this derivative stuff using the limit definitions of the derivative a lot more in the next few sections, and certainly in the next video, okay? So, wow, we covered a lot of stuff today. Can you remember what's the difference between average and instantaneous velocity? Well, average velocity, we said, was going to be s of b minus s of a over b minus a. But if we want instantaneous velocity, then we need to do the limit, and you pick which limit definition of the derivative you want to do. I'm going to use this one. H heads to 0 of s of x plus h minus s of x all over h. That will give me the general derivative, s prime of x. This gets me the slope of the secant, the average rate of change. This one is instantaneous rate of change. Because this lets the 2 points approach each other so that the distance between them is 0, this gives me the exact slope on that function at a given point. Okay? All right, then what did we do? Well, we also talked about these 3 limit definitions of the derivative. And I can't stress enough how you're going to see limit definitions of the derivative on the AP exam, and certainly on our next test and the test after that. So let's just one more time say that f prime of x, the general derivative, is the limit as h heads to 0 of f of x plus h minus f of x all over h. And then we had f prime at a certain point, the slope of f at a certain point. We want to know the derivative at a point. And that could be the limit as h heads to 0 of f of, we're replacing x's with a's, we replace x's with a's. Or we could also find f prime of a, we said, by using this other understanding where x approaches a of f of x minus f of a over x minus a. Okay? So you need to know how to use these limit definitions of the derivative to find the slope at a point. You also need to be able to find the slope at a point with your calculator. And we need to then be able to apply these derivatives. And the first way we apply them is by writing tangent and normal line equations. So you're going to, anytime you have to write the equation of a tangent or a normal, you need a point and a slope. And that slope is f prime of a. And then we can write our tangent line equation as y minus f of a equals f prime of a times x minus a. That's our tangent line equation in its most general form, right? So I have to plug in at what point for all these a's, and then I have to actually figure out what f prime of a is and what f of a is, okay? Well, I can't wait to take your questions and do more practice with you. See you.